So now we are recording, so everything you're going to be saying, we're going to hear it. All right. So, okay, so this is what we did yesterday. I just posted online because somebody sent me an email that they were not going to be able to make it to class because of doctor appointment. So what I've done is that now I think I changed the homework for even tomorrow and just take one PDF of it and upload it into Canvas. Okay? That way you have a copy for yourself. Okay, would that work? All right? So basically we did the first part of the homework, and I think I asked you to add to that homework to rewrite the equation of motion using the Lagrangian. Or did we finish the problem yesterday, the second one?
No, we never finished it.
We never finished it, so maybe let's finish that one before we move ahead. So that was the problem we started yesterday. I think this one we finished it. Okay. So this was the other problem we were solving over here. So basically we have the two pulleys and the block, and we need to derive the equation of motion, let's say, for the block and the pulley. All right. So let's see what we have over here. We have all these equations, T1 plus T2 minus MEG equal MX over dot. The other equation. We did this page over here. So we have the four equations from the free body diagrams. Then we went to kinematics. What did we get from kinematics? Okay, we got this relation. I think we start when we found the relation of XA with respect to XC over 2. All right. So that should be all the equations we need. Pretty sure. So let's say this will be equation 6. Okay, and now, in order not to waste too much time, let's do something here if you want. Let's look at the equations we have. And I think we should be able to do it. So this will be recording what is on the monitor. Okay. So I'm going to try to do something to save some time, okay? That way we don't have to use some software. So that was the first page we had. Now I'm going to switch to the computer, so you're going to see the computer. So maybe I'll go back over here. Home. Computer. Okay, I need to log in. Basically what happened now is that we have all the equations. Looks like all we need to do is to solve those equations. So let's see if we can do that a bit faster using software. All right, so here we are. Let's see if we can do this with Maple. Okay, so this is Maple over here. Let's say new document. Let me close this. A little bit. Okay, let me see if you can see all that stuff on the screen now. On the projector, yeah, it looks like we can get everything. All right, the other thing I have to increase the font, so I will do it. I don't know if I can do it from the beginning, or I need to do it later on. Say 22. Okay, so let's say first thing I do is restart. And now the other thing I'm going to do is just type down the equation. So equation 1 is what? Was T1 plus T2 minus M sub A times G minus M sub A times, so let's call this one X. This is XA, so we want everything, so let's look at XA. I know it's double dot, so let's say X PT A. X, T. Let's see if it works that way. Okay, not very pretty, but better than having to do it by hand. So the equation 2 would be T2 minus T1 times R sub A minus, I need to put double I, otherwise everything is an imaginary number, times beta, cannot put TT over here, so minus theta, okay. Let me put the accelerations right here. We're going to do this, and we know then there will be the second derivative. It will be easier. A, yeah, but then alpha times A. So this is the second equation. Third equation is T2 minus T3 times RB minus II of B times alpha B, column. Equation 4 is T3 minus MC times G minus MC times A of C. Okay, so these are the four equations we got from summation of forces and summation of moments for. Okay, so I have a problem here, it's not changing the font, so let's see. I made it afterwards, so it's into. Okay. So now the equation 5. What is our equation 5 over here once we go to kinematics? I think we can say it's just 2 times RA times alpha A plus RB times alpha B. Okay. And equation 6 is the one we just said, so do we need to do that one? Maybe not yet. Okay, equation 6, we could look at the accelerations. But let's look at it this way for now and see what happens. So let's say now we have solve. See what happened here, I think it's this way. So we're trying to solve those 5 equations. Okay, let's see what will be the unknowns we're trying to solve here. We're trying to solve it here for T1, T2, T3. What else do we need to solve for?
XTT, or I guess it would be A.
Yeah, acceleration of A, no?
Mm-hmm.
1, 2, 3, 4, and the acceleration of C?
Mm-hmm.
Okay, so we do that. Let's see what will happen. Really, what I'm trying to really what we need to solve for here, if I look at the first equation, is T1 and T2, no? So we get T1, T2, we should be able to get the equation of motion for block A, and if we're able to solve for T2 and T3, we should be able to get, or for T3, we should be able to get the motion of the block, no?
Yes, sir.
All right. So really we need T1, T2, T3, so we probably needed just 3 or 4 equations. But let's see what is that going to give us. So what did I do here? Oh, I think I know what the mistake is. I think here's the comma. I didn't do anything. Let's see what happens. Okay, so let's see. Is that the right sequence to solve? I'm pretty sure it's not one. Alright, I changed this one for alpha, but should not change anything. Okay, I don't know what's happening here. Okay, so we need T1, T2, T3. We have those 4 equations over here. Okay, so it's not able to solve this one, 2, 3, 4, 5. 1, 2, 3. Okay, let me go back. This is what the equations we have over here. So we have T1, T2, T2, 3, 4, no, 4 problem with the 4 equations. Then we need to have one equation for so we wrote that one over here that relates alpha A, alpha B. Yeah, that's good. Okay. Okay, so I think I know what's happening here. So we go back to the monitor. So I think here at the end we have to solve for everything for these to work. So we have to solve here for acceleration of A and acceleration of C. So that means we have amino unknowns 1, 2, 3, 4, 5, 6, 7. So equation 6 and equation 7. Okay, so let's see what those 2 equations could be. So we have 1, 2, 3, 4 over here. We have this one over here. So I'm gonna insert a line. Let's see if we insert a line over here. Oh, let me delete this. All right. So let's see if we can solve this problem. Let me go back to the .com. Okay, we're coming to the .com. Okay, why this is not working? Home. Dot camera. Okay, should be. It's not showing, no?
No.
Not showing video. Okay, so computer, it's showing computer, laptop, but camera. There we go.
There it
I don't know what happened. So basically what happened before is that we spent time finding the relation between these ones, but after this expression here, the 5, really what we needed to do is to find the expression for the acceleration of C, and do the same thing here to find the acceleration of point A. So the same steps we did over here for the velocities, we need to do the same step for the accelerations, and that will give us the additional 2 equations. So if I go back to that, page 10, now I will write down the acceleration of point, so I need the figure. Okay, the acceleration of point C from point B would be AB plus alpha B cross R of C with respect to B minus omega squared B R of C with respect to B. But we already said that, I'm using the blue so let me know if you can see any difference. Not much at all, no?
Not much, but it is there.
Yeah, this one we're saying is 0 because omega is 0 and AB is fixed. So really this point here you have AC would be equal to IJK of 0, 0, omega double dot B, even though I will change it then on the maple again, but. And the position of C with respect to B would be as before, would be equal to R sub B 0, 0. So at the end, this is going to give us that acceleration of C would be equal to RB theta double dot B. Now that's the red. Here it is. So you want to remove this number here 6, and this should be really our equation 6. And next we need to find the acceleration of point A. We can do it from point P. Okay, and again, this time we cancel this one. I don't know if we did that one or not before. No, we did acceleration of Q. But basically it's the same process, so this will be now equal to IJK 0, 0, theta double dot A. It will be position of A with respect to B would be R sub A 0, 0. Okay, I'm getting all those things from the figure that we did on this page over here. Okay, this one. If you want to leave, I have time. I should have time today. I don't have to rush after the second class. I try to scan also these class notes, and I put them on Canvas, okay?
Okay.
So we have this, so this is going to give us at the end that the acceleration of A will be equal to R sub A theta double dot A. Okay, so hopefully with those 2 additional equations, we should be able to make the other one work. Otherwise, I will have to get back to you on this one. Running out of ideas on this one. So let's go back to the home computer, here on the monitor. No, this is not going anywhere. Computer. All right. And let's say our equation 6 over here is going to be acceleration of C minus R of B times alpha B and equation 7 do this thing. Equation 7 would be then A of A minus R sub A alpha A. We have the 7 unknowns over here.
Looks so.
Okay, I don't see what it, you just type in this, maybe I'm doing something wrong with the command. Let me try to go to the help then. Because just type in what I've done over here, not trying to do anything, you just substitute the values. Not this in the past. Let me see if I have one of the other classes. No, I do it in some of my other classes. Sure. I always save it. Not here. That's the one I would do the most often. Okay, it's not in here. Alright, so let's just see here. You see help, solve. Looks like you put the parentheses outside now. That might be the one.
Just, yeah.
So yeah, because, yeah, maybe that's the problem.
Yeah, it's like outside the curly brackets.
There we go.
Uh-huh.
So you see this is magic, huh? Give you the answer. That's what I'm doing with this. So the expression can be pretty complicated, no?
Mm-hmm.
So basically, I mean, if you want, we can still try to simplify it a bit more. But basically, what would be the equation of motion for A? Let's take this one now for the equation of motion of the block. We should take that equation here and let's see what will happen. Let me try another one here. Let's do some extra simplification. Let's say, let's do the extra simplifications in here. Let's say IA, let's see if that simplifies a little bit, would be equal to M sub A times R sub A squared. Okay, so I think for a pool it's really divided by 2, but it doesn't matter here, okay? And let's say that the I sub B, oh, we didn't use M sub B, no? At all. So, I mean, it's gonna add M sub B. Just trying to see if it simplifies a little bit. M sub B, M sub square. It did simplify quite a lot, no?
Oh, yeah.
So we do this. Basically, I will give you this file, okay? I will save it. So, the bad thing is that if I go back to the monitor, I'm not going to be able to see those values. Okay, so let me write it down, and then I show the screen. So, what we have to do here. So this will be. So I'll show you the page afterwards. So from Maple output, I will show you that page. What happens is that if I put now the monitor for the camera, I will able to look at the screen. We need to know T1, so T1 will be equal to what? M A times G divided by 2. T2 equals to M A G MP plus 2 MC, everything divided by M sub A plus 2 M sub B plus MC. So we can look at the equations we need. T1, T2, that's fine. And then for the pulley, we can use the equation in 4, other pages here. 7, 8. Okay, and for the pulley A, so block C. So let's just do this one, okay? We have these two expressions, T1, T2. Then you go down to the dot cam, dot camera. Oops. So I just copied these two expressions. And maybe we're gonna just do the equation of the block, okay?
All right.
So if we come here, we say here recalling equation 1, which is 1, T1, or this is the equation of the pulley, sorry, so let's do pulley and the block. T2 minus MAG equal to MA X A. All right? So here, all right, I know I'm going to complicate stuff, but let's make a decision now. We want to write down the equations in function of X of C or X of A. Personally, I think it would make more sense to write in function of X of C, no?
Agreed.
No on the block. So let's say we use X of C. So we need to find what would be the relation between X of A, X of C, which we found before, no?
Mm-hmm.
On that equation that we deleted the number 6.
That was -1/2.
So, yeah, I mean, I have too many papers here. 8, 9, okay, so, yeah, and we have from that relation over here, we know that X sub A was equal to minus X sub C divided by 2.
Mm-hmm.
So basically, over here we need to be careful, but we can basically say the same thing for the accelerations. But here, do we really need to, yeah, this will be correct. Yeah, that should be correct. So now, so basically what would be the equation of motion? You just substitute these values over here, no?
Mm-hmm.
This one into here, so we're gonna have this one into here, this one into here, that will be constant, this will be the weight, and this will give you the equation of motion for the pulley A, no? Okay? So equation of motion for pulley A would be what? So I'm just going to leave T1 and T2 as they are there. Let's write them down with equal to what? It will be M sub A divided by 2 X double dot C, if I move everything to the other side. And then we'll have here plus, all this will be a constant. So there is no X. You see, in this point, since we don't have any spring, we don't have any value function of X, no?
Mm-hmm.
So then the constant term will be equal to what? M, so T1, M, A, G over 2, plus T2, which is M, A, G, we could have factor about M, A, G, MB plus 2MC divided by M sub A plus 2M sub B plus M sub C, is that it? Minus M sub AG equal to 0. Okay, so now let's do the same thing for the equation of the block. So it will be fully A. Now let's say for block, we need to recall in equation what? Before, so for the block would be equation 4, which is T3 minus MC times G equal MC X double dot C. So, from Maple output, what is T3? Is 2 MCG MA plus MB divided by MA plus 2 MB plus M sub C. Okay guys, so you see it's a lot better to use Maple than to have to do all that stuff by hand, no?
Mm-hmm.
We'll be spending the whole class and maybe the next one.
Yeah.
Okay, what's interesting here is about the process. So at the end, then what would be the equation of motion? We just substitute T3 on the previous equation,
Mm-hmm.
okay? And that will be the equation of motion for the block. Do you have any question? All right, so if you want, I don't know if you did it already, but for the homework, to the first homework, I'm just gonna add the problem of the block with the pendulum at the bottom just do that one with the Lagrange method, okay? Because this one is gonna be a bit harder. I think it's, maybe now we just have the X dot, no? Just do one of them, okay? Just do the other one,
Okay.
all right? Okay guys, so this is really the difficult part about vibrations, to find the equations of motion. Then to solve them, I think is the easy part. But again, here most of the class will be emphasized on how to solve the equation, not that much on this. Because I know it's not very clear when you take the class, but really what should be the goal of the dynamics class? What we just did, no? When you teach dynamics, they teach you all the time, I mean, I don't want to teach dynamics, no, but teach you all the time to solve for one instant in time. They say take the value that alpha equal to this at that instant in time. I think it would be a lot more productive for you if people were saying, just find the equation of motion, and then just solve that equation at that instant, instead of in function of time. Because really the goal of dynamics is for you to be able to get those equations of motions that then you can use in what? In vibrations and in controls. What do you do in controls? By trying to control the motion of an object, no?
Mm-hmm.
If you don't have the correct equation describing the motion of that object, there's no way to control it. All right? All right? So that's always the most difficult part, to tell the truth. It's not that much to build, to do the vibration analysis or even to build the control system. The difficult part is to find a good equation of motion that represents accurately what is happening with that object. Once you have that, everything should be a lot easier. All right, so let me reorganize all those pages because completely got lost here. 1, 2, 3, 4, 5, 6, 7. page 11 over here. We go here now to page what? Oh, before we move to the next page, before I forget, let's do that with you guys, otherwise I know I'm gonna forget. Let's go to the computer again. So, I mean, you can still do the manipulations over here, but let me just save this file. So file, save as, let's save it on the desktop. So how you want to call it, ME400? This is homework 1, no?
Yep.
Homework 1. I save it over here. Now, let me just come over here. Go to this class over here. What do you want me to put it? Maybe I put it in the assignments here and I upload it and that's it. You see this, I just did that before coming to class. So files, uploading file. You want it there or somewhere else?
Here's fine.
It's fine. So you want to look at the file or have an example, you have it now over here, okay?
Okay. And remind me, when again is this homework due?
I think I put, we can check now. I can change it, okay? It's not a big deal. I think I put on for Thursday.
Okay.
Is that tomorrow? Do you want me to move it? I don't care.
Thursday's fine.
Thursday fine? Okay. Midnight, so you can do it whatever you want. Don't do after that because then it creates a lot of problems over here for me to upload it.
Okay.
All right. So now that I know I'm not going to forget about that table file that we just created, let's go back here to the class notes. So, .com. Okay, so I think we did not record that class, but so let's do a review. I think we started on the class notes, the solution, so I say solution, procedure or solution for this type of equation, no? X double dot plus omega n squared x equal to 0, or theta double dot plus omega theta squared theta equal to 0, correct?
Mm-hmm.
So we say what would be the general form, so we say procedure we did this in class, no? It was the first thing to do what?
Assume a harmonic solution.
Correct. Assume I'm using the blue now because the black is almost gone. So what is the harmonic solution is to assume something which is of the form of sine of cosines, but which is the same to see x will be equal to c exponential, I think I use minus lambda t. Okay? 2, we say we substitute into equation of motion. So basically we have what? X double dot. So x dot will be equal to what? Minus c lambda exponential minus lambda t. X double dot minus plus c lambda squared exponential of minus lambda t. So once we substitute into this equation here, we have, we have c lambda squared exponential minus lambda t plus omega n squared c exponential minus lambda t equal to 0. So after factoring out the c exponential minus lambda t, we get the graphic equation of lambda squared plus omega n squared equal to 0.
Mm-hmm.
Okay, well, this should be a review. Here we say, when is this equation going to be satisfied? Either this term over here is 0, no?
Mm-hmm.
Or the term in two brackets. So either c exponential minus lambda t equal to 0, which is the trivial solution, or the characteristic equation omega plus omega n squared equal to 0, which means that lambda equal plus minus I omega n.
Mm-hmm.
Okay? So then we found that the final solution then becomes what? X, c1 of t, over here would be equal to c1 exponential of minus I omega n t plus c2 I of I omega n t. Is that what we did the last class? Did I put before the positive or the negative? I don't know.
Doesn't really matter.
It doesn't matter, but it's to be consistent. Because I'm going to follow whatever we do next. I'm going to follow whatever you need to do. So, okay, so we keep it that way. Negative first, positive. I don't know what I did last time. This is just a review. Okay, this should be on the class. So now at the end, what do we say? In order to determine C1 and C2, you're going to determine C1 and C2 from
Initial conditions.
initial conditions. Okay, so personally, I like to do the solution the way we just did it here with the exponentials, okay?
Mm-hmm.
And I think we explained the other day that to me will make sense because in controls here, what would you like to do? You would like to reduce this term as much as possible, and what would you like to do this one? Increase as much as possible, because here the negative sign of the exponential is going to damp, or is going to reduce the response, not damp, it's going to take the response to 0. This one is going to make it to diverge, no?
Mm-hmm.
Okay? So you can see in controls. However, in most textbook, and it's true that in order to plot it, it kind of is easier to explain, we're just going to rewrite this expression in function of sines and cosines. Okay? So what is the relation that let us go from exponentials to sines and cosines?
Euler's relation.
Euler relations of Euler identities, correct. So that's all we're going to be doing now, some algebra. So I'm going to open that page. All right, so this will be page 13 now. So let's say using Euler's identities, which are what? E I theta would be equal to cos theta plus I sin theta, and exponential of minus I theta is the same thing, but with a minus sign, minus I sin theta. Okay, so if we substitute into the equation x of t equals, first we have the negative, no? I omega and t. What are we going to get? So this would be, let me take some space, it would be C1. Then this would become what? Cosine omega nt minus I sine omega it plus C2 cosine omega nt plus I sine omega nt. Or this will give that x of t. If we factor out the cosine, then will be C1 plus C2 cosine omega nt.
Mm-hmm.
And the other one will be plus I, so let's see, it will be C2 minus C1 this time sine omega nt. Or, this is generally the way it's written, A cosine omega nt plus B sine omega t. Where A would be equal to what? C1 plus C2, and B would be equal to I C2 minus C1. Okay, so we keep doing simplifying for understanding, that's all. So for a better understanding or physical understanding, right, physical understanding, the above expression can be further simplified as follows. So basically the idea is to write the expression x of t as the amplitude of the sine of omega nt minus a phase angle phi. So I'm first going to give you the result and then we'll do the proof, okay?
All right.
So I don't have space to do it, but this would be the expression if you want here where, so I say A and P is the amplitude and is equal to the square root of a squared plus b squared. This is the phase angle, and phi is equal to the minus the tangent A over B. So I know I put everything in there, but I think it's clear if I put it in one page and if I go to the next one. All right. Let me keep this page closed over here. All right. Page 14. So now, proof. Change markers, I don't click, so. Okay, so we're gonna assume that A, if we do the substitution, A equal to minus the amplitude sine of the phase angle, and B equals to the amplitude of cosine of the phase angle. What's gonna happen? So what was the expression we had initially? Remember the expression was what? X of t equal to A cosine omega nt plus B sine omega nt. Okay? So this expression will become what? Minus amp sine phi cosine omega sine t plus amp cosine phi sine omega nt. All right. So you remember the trigonometric identity. So trig relation. What is that one? Sine u minus b is equal to what? Sine u sine of u cosine b minus
Sine B cosine U.
yeah, sine b cosine u. This one doesn't write well either. So the above relation will become what? X of t
Equals amplitude times the sine of omega nt minus phi.
will be the amplitude, and then this will be sine, no?
Mm-hmm.
What will be u in our case? Omega and t, no?
Mm-hmm.
And b will be this angle over here. Okay, and to finish the proof over here, what should be x squared plus b squared? If we do this substitution over here on top.
Should be equal to amplitude squared.
Correct, because basically what you're gonna have is amplitude square of what? Cosine squared theta plus, oops, cosine square of phi plus sine square of phi, which is what?
1.
1. So that will tell you what did we say was the amplitude equal to?
The root of a squared plus b squared.
So square root of a squared plus b squared. Okay, and finally, A over B will be equal to what? Minus amp
Tangent to phi.
sine B divided by amp cos phi, which basically says what? That, what is the relation we wrote already before? That so this will give you what? That A over B is equal to what? Minus
Tangent to phi.
tangent of phi. Oh, so you see I forgot to add something on the end. So this will tell you what? Or phi will be equal to what?
Negative arctangent of a over b.
Tangent of A over B. So be careful because on the first one, I forgot to put the negative arctangent, okay? Because I run it out of space, I think I forgot to put here the minus 1. You can put tangent minus 1 or arctangent, no?
Mm-hmm.
Yes, sir. I think on the calculators they have a tangent, or I don't know. Okay, so all this effort for what? Because we did all this stuff for what? Because really this expression here is exactly the same as, or should have the same meaning as, let's see, as that expression over here,
Mm-hmm.
or this one over here, no? We just went through algebra, okay? But if you look at this expression and this expression, it gets a little bit more difficult if then I tell you, you know what? I know you were expecting that, but however, if you look at this expression here, what should be the shape of the solution? Should be
Sinusoidal.
the sinusoidal, so the sine function, and this would specify where the sine function, where the sine function starts, no? The
Mhm.
base angle. It starts at 0, or at 45 degrees, 90, or whatever that can be. All right? So what is the shape of the sine function? So that's all I'm going to do next. So all this stuff is only to show at the end that if we needed to plot the solution, I'm going to do that two figures here. I'm going to do what is the one? Okay, I can just do one. But the thing is that it's going to be a little bit difficult to plot it. So, all right. So wait a second because I might not be able to plot it very well. For copying, okay? I give it time. So this will be, sorry, this will be x of t. Sorry for that. What should be this? Omega and t, no? Would be like y equal ax,
Mm-hmm.
would be omega and t. And now what's going to happen is that our solution, so let's say we know we're going to stay between those two values. So what is sine of 0?
0.
0. So if phi was 0, where should the function start? Right over here, no?
Mm-hmm.
But what happens if it's not 0?
Then it starts at phi.
Okay, so it starts at phi over here. So let's say, yeah, it will start here. So if we start from here, we'll do something like this. Okay, and if you want to plot this should be look something, this should be going down over here, no? Like this, right? So if you want, we can put some values over here. I mean, maybe it's just gonna complicate it too much, I don't wanna add too much either, but. Or here, what should it be? At one angle is the sign 0. At 0, and what else?
2 pi, or any integer multiple of pi.
Okay, so that's a good question. So since you say that, I'm going to do what I wanted to do here. So let's say I'm going to go here. So I know I need to be from here and here. It's going to be difficult here. But basically, this would be like being on a circle, right? Let's say we're here. And imagine you have a point P over here. So if you think about it, if you think about this point over here, if you want, this would be the phi, which the phi will also be this space over here. Maybe I'm trying to put too much information on one figure, but all right. So what happens if we follow the point P? It will be 0. This will be what? Pi over 2. This will be pi, 3 pi over 2, and 2 pi, no? Okay? So we start from point P. This is point P. At the beginning will be here. So we start from here. At 0 will be 0. We go up, no? Through this line, we go up. What's going to happen at pi over 2? It's going to be maximum, no? It should be pi over 2. Now it's going to start going down again to 0. Where it will be 0? At pi. Okay? Now it's going to go negative. So where will it be maximum negative?
3 pi over 2.
So we have to here 3 pi over 2. And then we can keep going this way. No? If you want here, this is 0, then this value here will be what? 2 pi, no?
Yes.
Okay? And you can keep going that way. So the phase angle phi basically says that you don't start at 0 with the sine function. Okay? That's all that is saying. But the reason why I like to do this figure is that you see that this is harmonic because it's like staying in a circle, no? You just stay on the circle all the time, over and over. Okay? So one thing which is important over here is that what will be one cycle? Is when you go from, let's say, I think the easiest way is to say you go peak to peak, no? But you could say you could go from this point to this point, correct? Should be the same. All right, or to this point to this point. Yeah?
Yes.
So to go to the same point in two different, if you want, sine waves. Okay, so this would be one cycle. Okay, and one cycle, if you look at the figure, will be equal to what?
Once around the circle.
So one cycle,
It's 2 pi radians.
correct, is 2 pi radians. And how are you going to specify the amount of time that this is taking? It's going to depend on the velocity at which the angle changes, no? So that would be what? Omega n times what is called here tau, the period. So tau here will be the period. So let me try to give maybe different definitions. So what will be tau? Tau will be equals to 2 pi divided by omega n. Okay, so what would be the definition of this? Let's try to give it an explanation. So point P goes through a complete revolution, what you said before, or cycle. And what is one revolution? We said before is 2 pi radians. Okay? During the time require, let me say this stuff, require by the angle omega and t. So what is moving is omega and t, required by the angle to increase from 0 to 2 pi. Does that make sense? Yeah, so basically point P needs to go through the whole cycle, okay? In the amount of time that this angle over here, that it will not be phi, no? It will be omega and t. The amount of time omega and t, so maybe let me plot omega and t. Let's see if I have another color here. What would be omega and t, the angle on this figure?
It would be the angle between the red line and the line that says phi. I believe.
Okay, correct. So it would be this line over here. So this one doesn't work at all. Can you see it or not? That would be the angle omega t. So basically it's where we start with the point P. Point P is going to go through 2 pi radians. In what is the period? In the amount of time. What is the angle? Is omega n, no? Okay? So the amount of time it's going to take for the point P to go to the circle will be equal to 2 pi divided by the speed at which the angle is changing, omega n. Yeah? Okay. So now, what would be the units for the period?
Time units.
Time units, correct. It would be time units. All right, so tau units would be in seconds. Okay? Now, there is something here. I don't know if I introduce it now or later. I can probably do it now. Okay? I'll do it now. And the frequency is defined as what? So frequency will be equal to what?
Omega n over 2 pi?
Yeah, it's one over the period, so it will be omega n over 2 pi. So what will be really the units?
Inverse of time units.
Inverse of time units, which is
Hertz.
hertz. Hertz, not the rental company. Okay? I don't know if that's related or not, but that would be an interesting question, no, to try to find out. What time is it?
10 to 1.
And we should be done at what time?
I believe 1.
1. Okay. Okay, I'm not gonna do the proof. I think I posted some of the class notes online, no? The PDF file? Did I do that?
I haven't checked.
No?
I don't think so.
Nothing, there's nothing, okay. So I'm not gonna do the proof, okay? I have it here, but I'm not gonna do it. I think we're wasting, not wasting, but, you know, we cannot do absolutely everything. I give you scans of this, I give you these class notes. So, but I think it would be logical to say it now. All right. And we finish with that. So 16. Maybe we can, I mean, I think I cannot did it. Okay, if the response xt equals to amplitude sine omega nt minus p was rewritten as a state-based representation okay, what we'll have is what? Okay, remember what is the state space representation? We're writing everything in function of x and x dot, no? I'm not going, I will post those class notes, but basically what happens is that here you have, if you want x dot, here you will have x, all right? So this would be the shape of the representation, no? Of the circle. It would be going all the time throughout a circle.
Essentially.
Essentially, that's what it would be, no? So don't do it over here, but this is in this prime. So far, we haven't, this is not interesting for this. So don't add this one. But later on, what's going to happen? What do you think is going to happen to the response if we add damping?
It's going to shrink, essentially.
It's going to shrink. So basically, it will start from this motion, and then it will start going, it will start circling down to zero, no?
Mm-hmm.
Okay? But that's not what's happening now, so don't do those lines now, okay? So not for now. All right? But it will be interesting to look at those figures once you start adding damping. Those figures can be pretty representative because they can show you, you can see visually how fast they are going towards the damp solution. So if you have a control system, this will be another way. They see how fast is your system going to damp that response, no? All right? So we stop over here for today, and tomorrow probably will be a very important class where we're going to do the derivation of the same equation, this one. What is this one? Go back, so to the classic equation we had at the beginning. of this equation here, okay, or this equation of motion here, but this time we'll have what? This is the mx double dot, this is the term coming from kx, but we'll have one more term which will be x dot, which is the damping. Okay? So we have 5 minutes, so we have that little discussion. So what is damping? Somebody asked me to define what is damping. So there are multiple types of damping, but let's say the more common damping is the viscous damping. So let me know for you what is damping.
It's something that drains energy from the system, slowly reducing how much something oscillates.
Okay, so that's the definition. But basically the damping will also be in function of the movement of the object, no? So basically what the damping is doing is creating a delay between that the response is happening and when the observer, if you want, is feeling it, no? Or in your car. The damper, basically what is it doing is delaying the time that you will feel the bump on the road. Okay? So that's what the dampers are. The dampers you will see, they will always be in function, so at least the viscous damping will always be in function of the velocity. So meaning that it will create a difference in time between the time you have the events happening and when it's really when you are really feeling it, no? Okay? So viscous damping will be in function of the velocity. Okay, so I will add that term on the equation. We'll do that next time, and we go throughout the derivation. But the derivation is a bit long because what might happen when you are damping? So far, we did not have damping. Okay, we did not have that term. So the solution was either stable or unstable, no? So now what can be the cases when you are damping? It can still be stable, unstable, no? But you can have different cases for the damping. You can go directly to the damping, you can do the second term, if you think about it. Even if you have damping, what is that equation? Here. Even if we had one term over here, this term might be most dominant than this one, no? So the equation will diverge. Then this one is more dominant, will mean the response will just damp. Okay, will just go to zero, even if there was no damping. But what happens if you are somewhere in between? All right? There would be 3 cases that we have to study. And it's a lot of derivation to do. But that basically would be the most important understanding for the one that you're feeling. All right, so see you tomorrow then. Let me turn this off.